Hello everyone and welcome to the C++ tutorial. In this tutorial, I will explain you 3 must-know methods for computing Fibonacci sequence in C++. But before I start, let me immediately provide the answer to the following important question. Namely, you might ask me the following: why did I create this video? The answer is the following one. By studying techniques for computing the Fibonacci sequences, you can learn the programming principles and way of thinking that can be applied to many different problems. In this video, you will learn how to compute the Fibonacci sequences by using the following 3 techniques. The first technique is based on pure recursion, and as you will see later, it is the most inefficient approach. Then you will learn the approach based on vectors, that's more efficient approach, and finally you will learn one very important technique called memoization, and this technique is combination of vectors and pure recursion. And notice here what I said. I said memoization. Memoization is not memorization, however, the principle is very similar, as you will see later on. Before I start with the explanation, I would like to mention the following. Those of you who are my subscribers or who follow my channel know by now that I always create a post that nicely summarizes everything that I will explain in this video. And consequently, here is the post. This post contains graphs, explanations, equations, and C++ code. A link to this post is given in the description below. Secondly, it took me a significant amount of time, energy, and planning to create this video and this post. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's start. First, we give a brief summary of the Fibonacci sequence. The Fibonacci sequence is defined as follows. For a non-negative integer n, the Fibonacci sequence is defined by this equation and this equation. R of n is the Fibonacci sequence at n, and it's defined recursively by using this equation. And once this argument over here, n minus 1 or n minus 2, reach 1 or 0, they're set either to 1 in the case of r of 1 or to 0 in the case of r of 0. That is, when n is equal to 1, r becomes 1, and when n is equal to 0, r becomes 0. Let us now graphically represent the computation of the Fibonacci sequence by using the recursive formula. Let us write the recursive formula once more over here. We have that r of n is equal to r of n minus 1 plus r of n minus 2. Let us assume that n is equal to 5. This means that r of 5 is equal to r of 4 plus r of 3. That is, to compute r of 5, or this node over here on this graph, we first need to compute r of 4, or this node over here, and we need to compute this node over here, r of 3, that's also given over here. On the other hand, to compute r of 4, we also need to compute r of 3 and r of 2. This is because of our recursive formula, because r of 4 is equal to R of 3 plus R of 2. Now, to compute R of 3, we obviously need to compute R of 2, and we obviously need to compute R of 1. However, we actually don't need to compute R of 1, because if we go back to the definition of the Fibonacci sequence, R of 1 is set to 1. And that's why this is a yellow node or a yellow leaf, because we don't need to recursively compute R of 1. When we reach to R of 1, we simply set the value of R of 1 to 1 and we return the value. Similarly, in the case of R of 2, we don't need to compute R of 1 because it's automatically set to 1, and we don't need to compute R of 0 because it's automatically set to 0. By using the same principle, we can compute other branches, other nodes, and other leaves of the Fibonacci sequence. And as you can see over here, Fibonacci sequence is nothing less than a tree. This graph over here is very helpful and very insightful because it enables us to immediately write a C++ function that implements a recursive approach for computing the Fibonacci sequence. And the code is given over here. I wrote a function called Fibonacci recursion that takes as an argument n and returns uint, that stands for unsigned long integer. Let us explain this function. Let us assume that n is equal to 3. Graphically, this means that I am at this node. Since n is equal to 3, I will not execute this part, and I need to jump over here. Let's see what happens over here. Since n is equal to 3, this part is 2, and this part is 1. This means that I need to recursively call Fibonacci recursion for n is equal to 2, and I need to recursively call again this function Fibonacci recursion for n is equal to 1. Graphically, any call of the function or any recursion is represented by this link, and the value that's being sent is either 2 or 1. Let us focus on this case, and I will erase this part over here, and let's see what happens for n is equal to 2. Now n is equal to 2. This condition again is not being satisfied, so I immediately jump over here. Now, since n is equal to 2, this part becomes 1, and this part becomes 0. So again, I need to recursively call my function for 1 and for 0. Let me erase now this part over here to see, first of all, what happens for n is equal to 1. And I didn't erase everything, so I need to erase over here. And let's see what happens. Now, n is equal to 1. And obviously, this condition is satisfied, so here I return 1. What happens over here? This function will return a value. It is 1. So here I will have 1 back to this node. And since this is 0, again, I need to evaluate my function. So I will erase this part. and this is now 0, that is n is 0, and obviously again this condition is satisfied and I return 0. So in the previous node for n is equal to 2, this part will return 0 and this part will return 1. So here I will have 0. And by using the same principle, we can conclude that over here we will return 1. And that's the principle for computing the Fibonacci sequence by using the recursive approach. We recursively go from a large number to the smallest numbers, and when we reach 1 or 0, we return the value, and then we recursively perform this summation. What is the main issue with this approach? The main issue is that this approach is very inefficient, and the reason is the following one. Notice what happens over here. Obviously, to compute R of 4, we need to compute R of 3. However, we see over here that we have another branch for computing R of 3. That is, we will at least twice need to compute R of 3, and we will need to do that in a recursive fashion. So the code doesn't know that, for example, if we have already computed R of 3 over here, the code will still compute this branch recursively. So it will double computations. And look at over here what happens. You have R of 2 here, R of 2 here, and R of 2 here. So we will 3 times compute R of 2 in a recursive manner, and this will significantly slow the computation process. Imagine that you have, for example, R of 50, for example. You will have many branches, and in these branches you will have many sub-trees that repeat itself, and the computation will be very slow, as you will see at the end of this video. At the end of this video, I will time everything. I will time all the codes, and you will see how inefficient this purely recursive approach actually is. Okay, let's now try to develop a more efficient approach. The more efficient approach is based on vectors or on dynamic arrays. The idea is given over here. Instead of recursively computing the sequence, we can simply define a vector. I explained vectors in one of my previous tutorials. If you want to learn more about vectors, you can click over here and you can read a complete tutorial on vectors or vector containers in a C++ standard template library. However, let's go back to our original tutorial. So over here, I define a vector. Here's my vector. It's called Fibonacci. Initially, I push back inside of this vector 0 and 1. So what I will have over here, I will have a vector of 0 and another entry will be 1. And this will be n is equal to 0 and n is equal to 1. Then what do? I simply implement my recursion. That is, over here in this for loop, I implement this part. Consequently, for n is equal to 3, I will take 0, that is this part over here, and I will take 1 or this part over here. I will add them together and I will push back the result inside of my vector. Then for n is equal to 4, I will simply take 2 previous values, I will add them up, and I will push the result over here. And by repeating this procedure, we can fill in this vector, and the last entry of this vector will correspond to the Fibonacci sequence for n, and we simply return the back of our vector. That's the second approach. As you will see later on, this approach is way more efficient compared to the first approach. That is, compared to the recursion. Now, believe it or not, there is another approach, and this approach is a very smart approach for computing the recursion. This approach is actually the most efficient one. So, what's the idea? Let's go back to our original diagram. What happens over here? To compute R of 5, we need to compute R of 4 and R of 3. To compute R of 4, we need to compute R of 3 and R of 2, etc. Now, if we go down R3, we can simply memorize or store the values of R of n that are previously being computed. So if we recursively compute something, we can store that value in a vector. For example, we can say that if we computed R of 2, we will store it in a vector. Now, if we somewhere in our recursion reach again R of 2, we are not going to recompute it. Instead, we will simply take the value from our vector and we will use that value. Similarly, if, for example, somewhere in the recursion, we first compute R of 3, and this is the first time we compute it, we will simply store it in a vector. And the next time we need to compute R of 3, instead of going down R3 and doing everything recursively and wasting computational time, we will simply read the value from our vector. That's why this approach is called the memoization approach. Or it can be also called a caching approach, or it can be also called memorization approach. Notice that the original name is memoization. Memo, like a memo, like a memory, but it's not exactly memory, it's like more like a memo. Okay, so here's the implementation. First of all, we declare a vector of integer type called memoization vector that will store the computed values. It has a dimension of 10,000. Here I set 10,000 since I will not increase my n beyond 10,000. Even for, let's say, 1,000, it takes quite some time to compute the value. And over here, I will complete this vector with this integer. And this integer is minus 99999. So what happens over here? Initially, I have a vector where every entry is minus 999, 999, etc. This minus 999 means that, for example, if minus 999 is over here and this corresponds to n50, this means that over here I did not store R of 50. So when we see in our code minus 999 in this vector, this means that R50 is not computed previously. And if we compute it, and this is the first time we compute it, instead of this minus 999, we will simply write R of 50. Okay, so here is our memoization function. Takes n as an argument. Again, if n is smaller than 2, we either return R of 0, that is 0, or R of 1, that's 1. And over here, what do? We simply test our condition for first time computation. So, if we have previously computed the value of R for n, that is, if this is not equal to minus 999, this means that the value will be actually corresponding to the correct value of the Fibonacci sequence. We simply go over here and we return the value of the Fibonacci sequence for given n. Otherwise, the value of Rn has not been computed previously, and we need to compute it in recursive manner, and that's done over here. That's our recursion. Once we compute this recursion, since this is the first time we are computing this recursion, we fill in the value in our vector, that is in this memoization vector, and we simply return our computed value of n. And that's the whole idea. So this approach combines recursion and vectors and uses caching or memoization to avoid unnecessary computations. And that's it. This is the third approach. It's a very elegant approach, and this technique is also used in other applications. Okay, let us see how these three methods work in practice. Here is the code that I develop and that tests these three approaches. You can find this code by either going at the top of my post, and you can click over here to find the code on my GitHub page. If you don't like this approach, you can simply go back again to my post. You can go at the end, and here's the code. So you can simply copy and paste this in your C++ editor. First, I'm including the necessary libraries. This is the input-output stream library necessary for printing messages and values. The second library is the vector library necessary for declaring vectors that are part of standard template library, and this library called chrono is library used for timing the code. Then I'm using the standard namespace, and I declare this uint or unsigned long integer. Here is the function that implements the first approach based on pure recursion. Then here's the function that implements the approach based on vectors, and here's the function that implements the third approach, that is the approach based on memoization that combines vectors and recursion. Once I do that, I go to my main function. Here I set n to 30, and I define, or better to say declare, my clock t variables. They are start time and end time. They're used to time the code. Then I declare results for the first approach, second approach, and the third approach. I simply call them Fibonacci recursion result, Fibonacci vector result, and Fibonacci memoization result. And I store results returned by three functions in these variables. Then I declare everything here in order to include time for reserving the memory space for variables. That is, I define my start and end, and I don't care about the type of this variable, so I use this magic, basically, keyword called auto. And this auto will automatically look into this function, and it will figure out what should stand here. Should I have here double, integer, or whatever? We are not interested in that, so I simply declare the variables for timing start and end, and over here I simply declare variables by using the same approach for timing the specific functions. Since I have three functions I will need three variables that will store the resulting time. That is the execution time. Then I simply compute the solution by using the first approach. That is, by using the recursion. I set clock to start. Here I reset the clock. In between, I call this function, and I compute the time. Store, and I also, of course, store the result in this variable here. I do the same thing for the second approach, that is for Fibonacci vector approach, and I do the same thing for the Fibonacci memoization approach. Call the clock, reset the clock in between, call the function, return the value, and compute the time. Notice here that the time is expressed in nanoseconds. And I finally print the results. Over here I commented this part of the code. However, you can uncomment this part of the code if you want to see the variables stored in my memoization vector. This is good for diagnosing the code. However, I tested the code, works like a charm, and we don't need to print the values. And watch over here, if you print the values for large n, it will take forever to print all the values. So let us compile and execute the code. And here is the result. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.